Okay, so just stop me at any time, ask questions at any time. So this first part right here is just an overview. So we learn how to get the molecular formula into the structural formula. And then we said all electron pairs, whether they're bonding or non-bonding, repel one another, which ends up giving you the shape. So the shape of water is not tetrahedral, but the shape is actually bent. It's bent because of these non-binding electron pairs. And then to apply that to chemical behavior, we use electronegativity to find out whether you have a polar or non-polar bond. If you have a polar bond, which is anything electronegativity greater than 0.5, if it's 1.7 and greater, it's ionic, right? We use full charges. But if it's within the medium range, but like many bonds are, then they're polar covalent, and we put charges across the bond because the electrons are not shared equally. So oxygen, being way more electronegative than hydrogen, pulls the electron cloud away from the hydrogen, leaving a partial positive charge on the hydrogen. Instead of putting the negative charge right here on the atom, we usually move it out to the non-binding electron pairs because those are the ones that are actually negative, not the nucleus. So here's basically the procedure that we use. So the first 3 steps are to find out which really is the central atom, everything around it in a symmetrical way, and we write in the bonds. And then we have to prove that by counting up all the valence electrons, meeting the octet and duet rule. So we had several examples over here. Notice that with formaldehyde, we had to do a double bond. With oxygen, we had to do a double bond. The metals, this right here represents the ionic bond, whereas all nonmetals, like in a polyatomic ion, are covalently bonded. So then getting the shape. So let's think about the shape for a minute. What would you say this one is? Where's the central atom? Well, there is none. So there is no regions of electron density around the central atom because there's no central atom. So this is just 2 atoms bonded together, so it's called diatomic, and there's not even any bond angles. Now, just for an advanced view of this, is this a symmetrical molecule? The answer is no. So that means I look at the difference in electronegativity. If the difference in electronegativity between this green one and this black one is 0.5 or greater, then that's a covalent bond. That means it's a rocket, it's a dipole. If I fire that rocket, this thing is going to move, meaning that it's a polar molecule. So this molecule would be likely to dissolve in water, unlikely to dissolve in oil. A non-polar molecule, a polar molecule. Now what if you have some situation like this? So the central atom has 2 regions of electron density, so it's linear. Okay, so the bond angles are 180 degrees. You're getting this region of electron density is far apart from this one because they repel one another. So now, if these were the same, then it would be a symmetrical molecule and it would be a non-polar molecule, no matter what. If these bonds are different, one may be polar and one may be non-polar. In that case, it would be a polar molecule. If you recall in the case of carbon dioxide, polar bond, but because they exactly cancel each other, because it's a symmetrical molecule, CO2 was a non-polar molecule. What if we have 3 regions of electron density around the center atom? And we say it's planar and trigonal. And the bond angles are 120 degrees. So if we're looking at real molecules, that would be planar and 120 degrees. Let's see. Here's another one. 1, 2, 3 regions of electron density around that one. 1, 2, 3 regions of electron density around that one. Both of those central atoms are planar trigonal with a 120 degrees bond angle. Here's another one. Okay, planar and trigonal. Here's another example. Planar trigonal, planar trigonal. Now, if you look at molecules with more than one planar trigonal configuration, if these are all the same kind of bonds, this is a symmetrical molecule. So it doesn't matter whether these are polar bonds or not, it's going to be nonpolar. If, for example, I changed one of these, now that's no longer symmetrical. And I would have to look to see if these are polar or nonpolar bonds. If this one is polar and the other ones are nonpolar, it's going to be a polar molecule because you got one rocket there. The alternate would also be true. If these are all polar and that one's nonpolar, it's still not symmetrical. It's going to be a polar molecule. Then, finally, for Chemistry 100, not finally for Biochem, 4 regions of electron density. And the bond angles and the basic geometric shape are 109.5 degrees from each other. Okay, this is the first one that's 3-dimensional. So this particular one, if it's all the same kind of bonds, it's symmetrical, so it would be nonpolar molecule. If I were to take one off, this is no longer symmetrical. So if these are all nonpolar bonds, it's a nonpolar molecule. If the green one is polar and the other one's nonpolar, it's a polar molecule. And the same would be true if all the white ones were polar and the green one were nonpolar. It would still be a polar molecule. As dipoles, not symmetrical, it's a polar molecule. So now let's look at these 2 basic shapes here, and we'll start breaking them down. So this is planar trigonal, bond angle is 120. What if I had a molecule that was shaped like this? 3 regions of electron density, so 120 degree bond angles, but this is not planar trigonal anymore, it's bent at 120 degrees. If these are polar bonds, it's a polar molecule. If they're nonpolar bonds, it's a nonpolar molecule. If I were to take one more off, then it would simply be diatomic.
Excuse me?
Say again?
May I say the diatomic, there is any bond in diatomic?
This is diatomic now because there's no central atom.
So can we say there is bond?
That would be bent.
No, not
Right.
bent. I mean bound. There is bound or not?
What about the bonds now?
I mean, there is one bond or no bond?
For the diatomic, he's asking
Yeah.
if there is or isn't a bond.
There is one bond, yes. Otherwise, it wouldn't even be a molecule.
Okay.
So,
Answer your question?
well, on the paper it says 0, right, for diatomic. For numbers of regions of electron density.
Yeah, but there is no central atom.
Right.
So
I mean,
red means region of electron density around a central atom, but there is no central atom. So this 0 reds.
so can we see the bond angles is 0, or we have to say none, the bond angles?
Well, it's preferred to say none, because if you say 0, that implies something else, I guess. But none or 0, I guess, is fine. Yeah. But
So
there's no
both
bonding.
0 or none is okay, right, for the answer?
Yeah, it should be okay. But on an exam, you won't have a choice for 0 degrees. Yeah, so it's just a matter of semantics, yeah.
Thank you.
Okay, then looking at tetrahedral, so if I take one off, now it becomes pyramidal, and this is not symmetrical, right? Could be a polar molecule if there's polar bonds in it. If I take another one off, then it's bent. Could be a polar molecule because it's not symmetrical anymore. And if I take another one off, then it's Way's favorite one, which is diatomic. There is no central atom, so there is no bond angles. And the way to think about this is, what does the X-ray diffraction machine see? It sees this atom and this atom. It doesn't see these non-bonding electron pairs. It doesn't see electrons, it sees nuclei. So then going into the more complex one, if you have 5 regions of electron density, you do not meet the octet rule. It's an exception to the rule. And you have 3 different kinds of bond angles here. So here's 90, here's 180. If you look that way, you see 120. Okay? And so when I take this apart, these two are as far apart from one another as possible. So those are the most stable. So if I'm going to take one off, it's going to be from the equatorial position. And now the shape is seesaw, right? And it goes back and forth like that. If I take one more off, also from the equatorial, then I got T-shape, right? Like a T. If I take off one more, then it's linear. And a lot of textbooks will say linear triatomic, but triatomic is not necessary, it's just linear. And then if I take one more off, then it's simply diatomic again. There is no bond angles because it's just simply diatomic. So I'm going to go backwards now. Say this purple to white one is a polar covalent bond. This is not symmetrical. I have a dipole in it. This is going to be a polar molecule. Now, when I put this one back on, and it's linear, it has polar bonds, but it's a non-polar molecule. When I put another one back on, I get T-shape. Then these two could cancel, but this one doesn't. So it's a polar molecule. If I put another one on there, same thing. These two cancel, but those two right there do not. So it's a polar molecule because of these two. Then when I put the last one back on, this is perfectly symmetrical. It's a non-polar molecule. And if I go to 6 regions of electron density, again, does not meet the octet rule. And I don't remember ever seeing anything with 7 or 8 regions of electron density around it. It's just too crowded. It can't happen. So this is perfectly symmetrical. Doesn't matter which one I take off. If I take off this, now it becomes square and pyramidal. Originally it was bipyramidal, right? Now it's simply pyramidal. So this would be symmetrical and nonpolar. This would be asymmetrical and polar. Those 4 would cancel out, but there's nothing there to cancel out this one.
So there would be 6 regions, 6 reds, right? But only 5 atoms are surrounding.
Yes, right. So now if I take one more off, okay, now it's planar and it's square and it's perfectly symmetrical. So this would be a non-polar molecule. Now if I take one more off, okay, it's T-shaped, right? So these 2 would cancel, but there's nothing to cancel this one. So it's a polar molecule. If I take off this other one, now it becomes linear and it's symmetrical. So it's a non-polar molecule. If I take off one more, then it's diatomic. There is no central atom, so there's no reds, there's no bond angles. And because it's not symmetrical, this would be a polar molecule. Okay. I've seen atoms all over the place on my desk here. Okay, so we just went through that. So looking at this molecule right here, I'm looking at carbon number 4, and I have the model of this molecule right here. Here's carbon number 4 right here. I got 1, 2 regions of electron density. It's linear. Carbon number 3, 1, 2 regions of electron density. It's linear. Carbon number 2, 1, 2, 3, 4 regions of electron density. It's tetrahedral. Carbon number 1, 1, 2, 3 regions of electron density. It's planar trigonal. Now, if I look at this, this oxygen right here, it's not a central atom, so it doesn't matter, right? This oxygen right here does act like a central atom. It's got 1, 2, 3, 4 regions of electron density. 2 of them don't have atoms, so that's bent. So let's see. I think we did a lot of that. Now, going back to that same model that's in my hand right here, I put in blue all the bonds that are polar. So this part of the molecule right here is polar, and all this part right here is nonpolar. So I would predict that the bulk of this molecule is going to be it's going to be polar and will dissolve in water. This part doesn't want to, this part does want to, but there's enough that wants to that it will dissolve in water. Now, how much is a different story. If you compare it to cholesterol, it's almost entirely nonpolar, so it doesn't dissolve in water very much at all, which is why people say it precipitates and forms plaques in your arteries if it's at extremely high concentrations. So then I gave many examples in here. Let's look at this one right here, carbonic acid. Somewhere in here, I made a carbonic acid. There it is. Oh, here it is. Okay. So here's something similar to carbonic acid, but I don't have enough of the different colors to make what I want. So just pretend that all three of these are oxygen, okay? So this is a center atom with 1, 2, 3 regions of electron density, so that should be planar and trigonal. Each one of these has 4 regions of electron density. 2 of them don't have bonds, so it's bent, okay? So now, if I look at it like this, does that look symmetrical to you? Now that's a rocket, and that's a rocket. If you allow even these 3 right here to counteract each other and neutralize one another, those rockets are not 180 degrees apart. It's going to move. There's really no way to make it like that. So no matter what you do, you can't make it symmetrical. It looks symmetrical if you look down like this, but these are rockets and they're not 180 degrees to each other. They don't cancel out. There's nothing you can do to make it cancel out. So this is a polar molecule and it will dissolve in water. Okay. So then I went through some organic ones. And I gave them to you on the homework, but really, nothing over here is, if I added another carbon over here, it would look like this one. And this didn't change at all. So at least you have some experience with organic molecules. After teaching organic chemistry, biochemistry, and general chemistry for many years, it's like there's an artificial separation between organic chemistry and general chemistry. It's artificial. Shouldn't happen. This makes things more complex. Okay, so any questions on chapter 10 at all?
So when you're naming or trying to figure out what the geometry is going to be, you can't really rely on the fact that like a tetrahedral will most likely be symmetrical. You have to look at the atoms involved.
Yes, you do. Yes, you do.
Okay.
Yeah.
But most of the times, if they're all the same atom, it'll become a non-polar because they cancel each other out, like a tetrahedral.
You know, you really have to look at every single one, every aspect of it, and make the decision. You can't like say, oh, they're all like this, or they're all like this.
Okay.
You can't do that with people either, right?
Mm-hmm.
So, you know, don't be prejudiced against molecules.
Okay, thanks.
Okay, so here's number 11, chapter 11. So much of it was review because this really is a difficult concept. So I reviewed the different bond angles. You can see that the actual ones are pretty close to oftentimes the theoretical ones, right? Based upon just the geometric shape. Some of them are exactly like that.
Does the T-shaped molecule have a 90-degree and 180-degree?
Which molecule?
The T-shape?
Okay, okay, ask again about the T-shape.
Does it have a 180 and a 90-degree bond angle?
Yes, it
Or is
does.
it just 90? Oh, okay, it's both.
180 and 90. Yes, it does.
Okay.
Okay, so in resonance, you guys okay with resonance? I mean, looking for ozone. So before I made this double bond over here, that electrons are over here. And the only reason I made that double bond is so that the central atom would have 8 dots around it. But I could have made the double bond here, or I could have made the double bond here. So without moving the atoms around, I got 2 places where I could put the double bond, so therefore I have 2 resonance structures. And just to be clear, because of the resonance structures, this is not really a double bond. That's not really a single bond, because both of those bonds turned out to be the same. So we say that each of those is about 50% single bond character and 50% double bond character. Let's see.
How would this look like for a question? I think I might have not seen these questions. Like, how would this look like as a question if you were to ask us about resonance?
Well, if it was a paper exam, I'd say give all the resonance structures for ozone. And you'd have to write 2 of them.
We would just put 2, right?
Right.
Okay. And then would we need to put the percentage?
That could be a question too.
Okay.
So here I might ask, well, draw all of the resonance structures or draw another resonance structure, just so I know that you know what a resonance structure is.
Yeah. So pretty much if you were to give us the first one, we would just draw the second one.
Well, you have to take this and come up with this, right?
Yeah.
So, yeah.
So we're gonna see these, like the actual Lewis structures on the test, this next test?
Well, you're going to be asked, because there's no way for you to draw the Lewis structure, you're going to be asked about the Lewis structures. Similar how you could draw resonance structures on the PDF type homework if you printed it out, but when it came to turning in the homework, you had to just answer questions about it, right?
Okay.
So, yeah. So then I went through all the polyatomic ions, and this is just background knowledge. When you get to another chemistry course, you'll be amazed how much this stuff has advanced your understanding. But not much of it's going to be on the exam. Okay, and then we went crazy over here, talking about lemurs and free radicals and all this kind of stuff. But again, it's all in a red box, right? On Friday night, we have like a Pauhana. We've been doing this for years, but now we've been doing it online. And most of them are nutritionists and biochemical nutritionists and dietitians and all this kind of stuff. And we were talking about this, and I showed them the structure of this, and they were all blown away. And they agreed with me that, you know, Chuck Norris jokes should come back, even though your guys' generation doesn't know who Chuck Norris is.
I literally know Chuck Norris just due to all the memes.
Yeah.
I've never watched a Chuck Norris movie.
They are kind of funny, you know. It's like Steven Seagal. It's the same thing. You watch the Steven Seagal movies. It's like, wait. How many people did you kill in this movie? And now you're talking about peace and getting along with everybody? Ridiculous. And it's hard to say the same thing about Bruce Lee, though.
For the Lewis structures, when you're drawing them, if there's any metals, you draw it with those. You draw the cation or anion by itself with the bars, right?
Mm-hmm.
You don't connect them. Okay.
Right. So for our class, never draw a covalent bond between a metal and a non-metal.
Okay, it's always going to be separate. Okay.
I know you weren't planning on doing that. I'm just saying that, don't do that. You can do it outside of the class. Okay, so we can predict the products of a reaction pretty well. Like I said, for biochem, I put some of that on the homework. Chemistry 100, I did not. But I'm not going to put any like this on the exam. So you'll just be asked to balance reactions. So similar to the homework.
So you know how the homework's not available anymore? You said that so we'll have the keys so that we can go over the homework still?
Yeah, they're in resources.
Okay.
Yeah. Yeah, so occasionally there's issues students have with identifying what kind of reaction it is, but not very often. In the solubility rules, you do not need to memorize, but know what it means. So if you see a reaction like this, right? How do I know if this reaction is going to happen? It's going to happen because I'm seeing that this is a precipitate over here. It formed a solid. The reaction was happening up here. That gets removed. So it cannot redissolve. It cannot reverse itself. Every time you form one, it's gone. So it drives that reaction towards completion.
For the chemical or the reactions, only 4 of them are redox reactions, right? The synthesis, decomposition, single displacement, combustion, and redox.
Actually, everything is a redox except for double displacement and acid-base reactions, because acid-base reactions are double displacement reactions.
Mm-hmm. Okay.
But like if you look at this one, right? Here's an element. Now it's not an element anymore. That oxidation state was 0, and now whatever it is not 0, so it's a redox reaction.
Could you also go over a little bit about how to identify what's being reduced and what's being oxidized?
Sure. So if I'm looking at this reaction right here, I'm really thinking about electronegativity. So the electronegativity for nitrogen is like 3.04, whereas hydrogen is only 2.2. So looking in the bond over here, you're pulling electrons from the hydrogen to the nitrogen. So you don't have to completely remove it, but if you pull it away from it, you're oxidizing it. So if I drew an arrow from here to here, you would see that electrons are going from the hydrogen to the nitrogen. Not completely, because it's a covalent bond. So hydrogen is getting oxidized, nitrogen is getting reduced. If hydrogen is getting oxidized, what is the oxidizing agent? It would be nitrogen. So if nitrogen is getting reduced, in other words, getting more electrons, what's reducing it? It would be the hydrogen. Hydrogen would be the reducing agent.
Okay. Did they have to call it reduced? That always confuses me.
Well, you know, it's interesting how chemistry is. That is, what I just said about this was true, but a lot of people wouldn't say that. But when it comes to this one over here, oh, they'd all be saying that oxygen is the oxidizing agent. It's a similar thing here. If you look at the bond between oxygen and hydrogen, oxygen is extremely electronegative, so it's pulling electrons towards it. Okay? So that means the electrons are going from the hydrogen to the oxygen. So oxygen is getting reduced. What's the reducing agent? Hydrogen. Hydrogen is getting oxidized. What's the oxidizing agent? Oxygen. So let's see, what else? Oh yeah, molecular, photoionic, net ionic. Anybody have any issues with those? And I will say that this is hard in a way because, you know, chemists assume that you guys are also chemists, right? That's the problem. That's an acid. We didn't cover acids yet. But acids, what do? They ionize. That's what they do. Okay, so that's a strong acid, so that's how you would find it. And there's no way you would know that hydrocyanic acid is a gas. You would have to observe that in the reaction.
So for all of these, like let's say it was on a quiz or on the test, we would just be balancing it.
Yeah, and then you know, answering what is the type of reaction.
Okay.
Would the reaction happen?
Yeah. How do we know if a reaction would happen or not?
Because you see a gas being evolved here.
Oh, I see.
So the reaction is happening here. The gas is escaping. It's not going to go back.
Yeah.
Okay. So those are some of the things that I was, you know, pointing out to you folks, so you will know that. Otherwise, you won't know that. And I know. Good luck finding that type of stuff in another book or something. They don't normally do it, if at all. And with the activity series, of course, you do not have to memorize this. But you should know what the jewelry metals are. You have some experience with iron and lead and things like that. So let's see. The neutralization reactions, they also are double displacement, because here's a compound and a compound, and then you go and form a compound and another compound. But the way that I taught you to balance these that are different than the other ones is taking advantage of the fact that acids give H plus, bases give OH minus, and they love each other. So they're going to form water, right? Very reactive, stable. So Here I got 2 hydroxides, so I'd have to put a 2 here so I can get 2 hydrogen ions. And when I do that, I'll get 2 water molecules. So here's the balanced reaction. You can see what's left over is like, I got to do something with the magnesium. I got to go do something with the chlorine. Well, guess what? You know how to do that because you know how to make neutral compounds. That was in previous chapter. In combustion reactions, I see sometimes students have a problem with this kind, where they get more complex, you end up with a fraction. So then you have to multiply the whole equation. I mean, think of it as an algebraic equation because that's exactly what these are. That arrow, simply replace it with an equal sign. Instead of using 2x and 13y, right, you just use chemical formulas.
Combustion always has the O2 though, right?
Yeah, you don't want to have it with half of an oxygen molecule or something. And anything with oxygen is an element, then it's not an element, that is a combustion reaction.
So is it basically if you see an O2, your first instinct should think combustion?
Yep.
Okay.
Mm-hmm. But if you go back over here, let's see. Look at this reaction right here. What if this was reversed? I'd have 2 hydrogen plus oxygen and would go to water. You could say that was a synthesis reaction, but you could also say that that's combustion, isn't it? So oftentimes we have reactions that, can be categorized more than one way.
So all 3 reactions could happen, but will there always be one that like predominates the other ones, like one that it favors?
Well, you don't have to make that kind of distinction.
Okay, never mind then.
Yeah, if you become a chemistry teacher, maybe. So looking at this reaction, do you think this reaction would happen?
Yes.
Because
You're forming water and carbon dioxide that are stable.
yes, and what do you know about oxygen?
They're super reactive.
Super reactive, that's right. You're getting this. So that sounds like I'm trying to take credit for your learning when you should have the credit for learning.
No.
Oh, so pretty much the way to tell if something will occur is if the product is super stable.
Yeah.
Mm.
Yeah. Like I was saying, when we were trying to figure out what the products would be, I said it's going to be something that's stable. It's going to obey all the octet and duet rules, and because you don't form things that are not stable. You don't have a bunch of elements that's sitting around and all of a sudden they turn into a bomb. Doesn't happen. A bomb might go the other way, turn into elements.
Because it wants to be stable.
Yep.
Okay.
So anyway, we might go back to chapter 9 to review all the stuff about assigning oxidation numbers. And so here's some more practice with that. Elements are always 0. Ions are equal to their charge, right? So if you just do that and you say, well, this was 0 and now it's +2, what happened to it? It got oxidized. That was +1, now it's 0, it got reduced. So electrons went from the copper to the silver. And why did that happen? Why would this reaction happen? Because silver is more stable than copper. That's why that happened. So here's where I talked about all that stuff again. So why will this happen? Simply because you either see this energy given off, or even if you don't see that, you know from everyday experience that, you know, you do combustion with methane, you get energy from it. So that's what tells you that the reaction is going to go that way. Then here's a precipitate, here's a gas, and of course you can use the activity series. Okay. And some of the activity series is in your everyday experience. So say you found somebody that you really liked, and notice that I'm not using the terms boys or girl or anything like that. And so you're going to go buy that person some jewelry. You're going to buy them something nice. Are you going to buy something reactive or something stable? So anyway. Just by the way, I'm getting so hypersensitive to all these words that we normally use, like boys and girls. So one of my good friends, she works at a nonprofit where they help disadvantaged children, and they work out of the, you know, the housing and stuff. Oh, they're not allowed to refer to them as boys and girls. They have to refer to them as children. It's just so out of control. So this last part is getting you really ready for, you know, the next chapter in the next unit, right? So I just took this basic stuff out of the other units so that, you know, you get more time to deal with this stuff. So the molar mass is simply the mass of 1 mole of something. And that something could be atoms, molecules, or formula units. And so these are the molar masses: the gram atomic weight, the gram molecular weight, the gram formula weight. But if we don't have the gram in front of it, we're not talking about a mole, we're talking about a single unit. So atomic weight means the mass of a single atom. That would be in terms of AMU. And going back to the periodic table, we call this the atomic weight. And a lot of physicists over the years have said, why do you guys still use the word weight? We use mass. I said, because we have multiple meanings for that. If it's one atom, it has 15.9994 atomic mass units. That's an individual atom. If we use grams, then that's a gram atomic weight, which is the molar mass. So you should know how to calculate the molar mass for more complex compound, for example, like that. And then you should know how to calculate the percent composition. It's just one extra step, right? So for example, to calculate the percent magnesium, there's about 73 grams of magnesium in the compound, and the compound is about 263 grams. So that's how I get the percent magnesium. So for exam 3, we're going to have 3 tools in our toolbox. You've used this several times before. We've used this a couple times before. We've used this a couple times before. And so what's in the middle of everything, if you want to go from here to here or from here to here, you got to go to moles. So if you look at some of these problems, we're using the units to figure out what we need, but in our mind we're thinking, which conversion factor is it going to be? I might have to do 2 conversion factors. Which one am I going to use first? It's only one of these 3.
Sorry, when do we use these again?
You use them when you need to. So like, take for example, this one. How many formula units in 6 grams of magnesium phosphate if the molar mass is given? The molar mass is a conversion factor, isn't it? That's this right here. And so they're asking to go from grams to formula units. So here's grams, here's formula units. What do? I got to get the moles. So I need to get rid of grams and keep moles. So grams goes on the bottom, moles goes on the top. Now I'm moles, I'm right here. What are they asking again? How many formula units? So that's Avogadro's number. So I have to get rid of moles, right? And keep formula units, which is on the top right here, and that's my answer. So 2-step conversion, just like going from, say, millimeters into megameters, you went to the base unit first, right? So in a way, the base unit here is simply moles. Okay. What about this one here? So how many grams of phosphorus and 6 grams of magnesium phosphate given the molar mass? What are we doing here? We got grams of the compound. We need to get grams of one of the elements. I'm going to have to do this conversion. So how do I do that? So I got 6 grams of magnesium phosphate. That is simply a conversion factor, right? So I first have to go to moles. Then I got moles of magnesium phosphate. What do they want again? They want grams of phosphorus. So I got to go from moles of magnesium phosphate, get rid of that, go into moles of phosphorus. So now I got the moles of phosphorus. So then I can just use basically from the periodic table to turn moles of phosphorus into grams of phosphorus. So I don't know if there's anything more over here. Yeah, that's it. Okay. So let me try something and see if this works. Okay, so there's water. The central atom would be oxygen. Now to draw in a 3-dimensional manner, I'm basically going like this. So you see how I have those 4 regions of electron density in a 3-dimensional manner? And I could put hydrogens on any 2 of them. And this bond angle right here would be what? 109.5 degrees, right? And these would simply be my electron pairs, the non-bonding electron pairs. So what if I did, let's see.
Those triangles basically just represent bonds, like, right?
Yeah, but this
Yeah.
one's coming out towards you. This one's going away from you.
Yeah, it doesn't like the non-bonded electrons don't need to be on the shaded ones. It doesn't matter. They're basically the same, except they're just showing depth.
You could do, yeah, you could do it that way too.
For some reason, I thought that you had to put the non-bonding electron pairs on the triangles.
Nope, don't have to.
Okay.
We're just trying to show that it's three-dimensional on a two-dimensional surface.
Right.
So if we took something like carbonate, right? Well, first of all, I got to put this in some kind of brackets. And there's going to be a -2 over there somewhere. And then the central atom would be carbon. And then I got 3 oxygens around it in some kind of a symmetrical way that are all bonded. Then I have to come up with the number of valence electrons. How come I put, it's supposed to be a 3 right there. Still learning my letters when it comes to iPad. So then I put in all my valence electrons, and I would end up having, let's see, like that. The extra 2 that came from here, right? So then I have to put a double bond somewhere. So I have to take these away maybe and put a double bond there. Okay, so I got 1, 2, 3 regions of electron density. So that should be trigonal and planar. Planar, trigonal, however you want to say it. Okay. Okay. Anyway, anybody have any more questions?
Are molecules that only have carbon and hydrogen, are they always going to be nonpolar because the electronegativity difference is too small?
That's exactly right. Yep.
Thank you.
Yeah. So for second summer session, when I have to do organic chemistry stuff, this iPad might be really helpful. We'll see. So if you have other questions, you're welcome to email me. I can look at email right now. Then I'll be lecturing from noon to 1:30. So then after 1:30, I'll look at email again. Okay?
Okay, thank you.
Thank you. Do good on your exam now.
Yes, we'll try.